In this video, I'm going to show how to run a molecular dynamics simulation of a protein in water using VMD and NAMD. So I'm going to be doing this in Windows. And if you need to see how to install NAMD in Windows and also run NAMD through Windows easily by adding it to your path, I have another video for that. So see that other video. So it's useful to create a working directory or working folder where we're going to run our simulation, have all our simulation files. So I'm going to make a new folder, and I'm going to call it MD for molecular dynamics. OK, so some of the things we're going to need to run the simulation are the CHARMM parameter files, which are available in the module. So I'm just going to copy those and put those into our working folder. Then we need to get our protein. And I'm going to go to rcsb.org. And I'm going to choose the protein 1E0M. And this is a small beta sheet structure. And so I'm going to download that PDB. And that's going to get saved to my downloads folder. OK, so now I'm going to move this. So I'm going to select the PDB file that I just saved. And I'm going to do cut. And I'm going to paste it into our working folder. OK, so now I have the PDB and these parameter files. So to run the simulation, we need to generate a PSF and PDB file for the protein with water and ions. So to do that, I'm going to first open VMD. And there can be some issues with the working directory used by VMD. So the first thing we want to do is move VMD into the folder that's our working folder. So if I go to extensions TK console, here we can type our command line. If we type pwd, this shows us where VMD's current folder is. And VMD is currently in C:/program files/University of Illinois/VMD. But we'd like this to be our working folder so that all of the output of VMD will go into our working folder. So to do that, we'll type cd. And my working folder is on the E drive. So I'm going to do E:/teaching. And you can hit tab. If you just type a few letters, you can hit tab to complete. And that's a good way to ensure that you type the name correctly. Then MD. OK, so now if I type pwd, we're in E:/teaching/MD. If I type ls, that shows me the files that are in there. And you can see my PDB file of the protein and also the CHARMM parameter files. So now I'm going to go to File, New Molecule. And when I hit Browse, we should already be in our working directory. So then I'm going to click on the PDB file and hit Open, and then click Load. So now we can look at our structure. If I go to cartoon, you can see that this is a small beta sheet protein. And to run NAMD, we need to generate a PSF and PDB file for this protein. So, so the first thing we're going to do before we do that is move the protein to the origin. And sometimes these PDB files will have other things like water that we don't want to include in our final structure. So we're going to make a PDB with just the protein. So I'm going to do set S atom select top protein. And so this is going to make a new variable called S that stores an atom selection of the protein in the top molecule. So this T is black here, so that means this is our top molecule. We only have one molecule. Notice that in TCL, we have to have the square brackets to do a command. So when I do this set S, atom select top protein, it will make a selection of the protein. If I do $S num, that will tell us how many atoms are in the protein. There's 586. And we can also select what frame we want to use. I'm going to go back to frame 0 here because this is an NMR structure that has multiple frames. So we want to move this protein so its center is on 0, 0, 0. So I'm going to set a new variable called C to the center of the protein. So I'm going to say set C, measure center, and then I'm going to use this selection, $S. And this will set C to the center of the protein. We can see that actually this C is pretty much near the center of the protein already. It's less than an angstrom from the center. But regardless, we're going to move this selection by doing $S, move by to the inverse of its current center. And by moving it by the inverse of its current center, that will set the center to 0, 0, 0. So to do that, we do $S move by vec invert $C. So that will switch all of the plus signs to minus signs and all the minus signs to plus signs, and should make it so the center becomes 0. So now if I do measure center $S, we get numbers that are times 10 to the negative 8th. So it's effectively at 0, 0, 0. OK, so then we're going to save this PDB file as a new PDB file, and we're going to call it, well, since this protein is a beta sheet, we'll call it beta sheet, or maybe just beta center.pdb. And then we do $S write PDB, beta center.pdb. OK, so this makes a new PDB file, which we can now load. And so here's our new PDB file. Now we're ready to create the PSF in PDB. So to do that, I'm going to go to the VMD window, Extensions, Modeling, Automatic PSF Builder. And you can see that this beta center.pdb is already selected as the input file. And then the output name will be beta center auto PSF. We can just say include everything, though protein is also fine because this is just a protein. And then we're just going to click, I'm feeling lucky. OK, so now it created beta underscore center underscore auto PSF.PSF and PDB. So this gives us the PSF and PDB structure for the protein. And this PSF structure is important because it contains all the information that we need to run the simulation. The PDB is just used for coordinates. So let's take a look at that PSF file. So to do that, I'm going to use WordPad. It's not exactly the best tool for a general text editor, but everybody has it. So that's just what I'm going to use. So I'm going to search here for WordPad. And OK, so I opened WordPad. Then I'm going to go to Open and select so I need to change this from WordPad documents to all documents. And then I'm going to select the PSF that we just generated. So this is beta_center auto_psf.psf. OK, so this PSF file contains all of the data that NAMD needs to run the simulation. And in the assignment, I asked for certain parts of this file. So the easiest way to find the different parts of the file is to do Control F and do a search for exclamation point. And all the different sections of the file contain an exclamation point that tells us how many entities for that section of the file we have. So the first section of the file is the atoms. And you can see we have 584 atoms. If I hit Find Next, we go to the bonds, and there's 596 bonds in this file. Next are the number of angles. There's 1,062. And there's dihedrals, impropers, stuff that NAMD doesn't use. And then there's cross terms here. So in this structure, we have 35 cross terms. OK, so that PSF file looks good. The next thing we want to do is add a box of water to this simulation structure. So currently, my top molecules is beta center auto PSF. Then I'll go to the VMD main window, select extensions, TK console, which I already have open. And so let's look at how big this molecule is so we can sort of decide how big our water box should be. So I'm going to hit 2, which is going to allow me to select distances. So I'm going to click this atom here, which looks like it's at the farthest extent of this protein. And then I'm going to go down here and click this atom. And you can see that the longest length along this protein is something like 33 angstroms. So 33 and a half. So I want my box to be of water to be at least big enough that there's maybe about 10 water molecules on each side. So or 10 angstroms of water molecules, or 8 to 10. So to do that, I'm going to solvate, and I'm going to make a cubic box for this protein that's going to be 50 angstroms by 50 angstroms by 50 angstroms. So to do that, I'm going to use the solvate command. And I have to tell the solvate command what my PSF and PDB files are. So I called these beta center auto_psf.psf and beta center auto_psf.pdb. And then I'm going to do -min-max. And here I need to give the vectors that or points that represent the farthest extent of our box. So if we want it to be 50 by 50, this should go from -25, -25, -25. So those are the X, Y, and Z positions of the bottom left outward corner, and then the top right inward corner is going to be 25, 25, 25. And then we can also do -O to specify the output. And for the output, I'm going to call it beta_water. OK, so now I'll hit Enter, and VMD should add this water box. And it seems to be working. OK, so now you see that the structure beta_water.psf has a protein in a box of water. Okay, to make this a more physiologically realistic system, we're going to add some salt to the solution. And in the assignment, I asked you to do a particular concentration, but typically we're going to use a concentration that's something like 150 millimolar of sodium chloride. This isn't exactly what you have in blood or interstitial fluid, but it's fairly similar to that. There's lots of other ions and small molecules, but sodium and chloride are the most common constituents after water and interstitial fluid. So we'll go to modeling, add ions, and the PSF is beta_water.psf. The PDB is beta_water.pdb. We'll call the output beta_sol for solution. Our salt is going to be sodium chloride. We're going to choose neutralize and set the sodium chloride concentration. And for this, we'll do the default, but you should check what I ask you to do in the assignment. So default is 150 millimolar, or 0.15 mole per liter. And then we can just hit auto ionize. Okay, so we then have a new structure here. So I'm going to stop showing the water structure and show our new structure. And then I'll go to representations. And our new structure is beta_sol.psf. I'm going to hit create rep. And I'm going to make my selection ions. And then I'm going to select drawing method VDW. So now we can see the ions in the system. So the sodium ions are shown in yellow, and the chloride ions are shown in cyan here. So we have a few sodium and chloride ions in this system. Okay, so we've generated a PSF and PDB file that has the protein in a water box and with some ions. So that's basically what we need to run our simulation. So the next thing we need to do is make a simulation configuration file. So I gave you an example file, but we need to make some alterations to it. Okay, so well, now you see there's a lot of files in here. So my example is this run.namd. Okay, so I'm going to open that again with WordPad. Okay, so I again need to change this to all documents, and I'll find run.namd. Okay, so this first step, we're going to run the minimization. And to do that, we'll have the output be called min beta, so that we know what simulation this is. So this is going to be the minimization of our beta sheet protein. And then for number of steps, for the minimization, 500 steps is enough. We don't have these coordinate files yet, so I'm going to comment that part out by adding this #, which is the comment character in TCL. Our structure is going to be the name that we made for the PSF file, which was beta-sol.psf. The coordinates are going to be beta-sol.pdb. You'll notice up here that I defined a variable called temper that I set to 295. So that's near room temperature in Kelvin. And then I'm using this variable for the Langevin temperature and the Langevin piston temperature. This actually doesn't matter for minimization because the Langevin thermostat and barostat aren't actually used, but we're going to need it later when we run dynamics. So these parameter files we've already copied into our directory. So this is the CHARMM 36M parameter set for proteins, and these are the CHARMM parameters for water and ions. And it's going to write the output every 100 steps. So I think that's about everything we need to run the minimization. So let's see if that will work. So I'm going to hit save. Oh, well, I'm going to save it as, I'm going to give it a different name. I'm going to call this min beta.namd. And then I'm going to hit save. Now, we should now see this min beta.namd here. And if I open a terminal, and if you followed my other video, if you type NAMD2, you should get NAMD to run. But then it should say no simulation config file specified on command line. So we need to specify the config file. But first to do that, we have to go to our working directory. So I'm going to do cd /teachings/MD. Or maybe I need to type : first. OK. And then cd. OK, well, it looks like I'm already in the directory. So from here, I can type dir and see what files are in here. And a thing that's important to notice is even though in Windows Explorer, this file is called min_beta.namd, WordPad saves it with a .txt that's hidden. So you have to watch these things in Windows. It tries to make things easier, but actually makes them harder. So when we run NAMD, we have to put this full name, which is min_beta.namd.txt. So let's try that. We'll do NAMD2 min_beta.namd.txt. And again, I'm using tab to complete. So once I write min_ and I hit tab, it should be able to complete it. So I don't have to type the whole thing. OK, so it gave me an error. And it says, error must have an initial temperature or velocity file. So let's go back to WordPad here. And we need to set the initial temperature. So to do that, I'll type temperature $temper. OK, so now let's try again to run NAMD. So now it says PME requires periodic boundary conditions. We forgot to tell it what the size of our system was. And if you remember, our system was 50 by 50 by 50. So we need to set cell basis vector 1, 50, 0, 0, cell basis vector 2, 0, 50, 0, and cell basis vector 3, 0, 0, 50. So this will make a cubic box that's 50 angstroms in each direction. So then I'll save it, and I will try again to run NAMD. And you can see it says NAMD stopped working. there's something else that I forgot. So this is supposed to be a minimization, and I forgot to put minimization on. So originally, the system is not yet ready to run the simulation because the system that we built has some often has clashes between atoms. So we need to run this minimization first. If we try to run dynamics first, like I just did, the simulation will crash. So I'll do minimization on. OK, so now we're ready to try to run this minimization again. Do NAMD2 min underscore beta dot NAMD.txt. And so now it's running. We can tell it's running because the step number, which is the first number after energy, is going up. So, so this number is, we're at about the 100th step now, 110, 120. So we're running 500 steps. So we just need to wait for this to finish. This minimization really isn't a real simulation. It's not real molecular dynamics. It's just something we have to do to get the system ready to run molecular dynamics, because we build our system in a way that doesn't end up being very natural. There might be clashes between atoms. So this third number down the column in these energy outputs is the total energy. And as the simulation goes in this energy minimization, this total energy should go down. So, so our simulation just finished, and the final total energy is minus 43,435. If we go up to the last frame we can see in the terminal, be step 478, there we had minus 43,319. So you can see that the energy minimization did what it was supposed to. It reduced it from minus 43,319 to something that's less, minus 43,435. So let's go into VMD and take a look at the output of the minimization. So if we look in our working directory, we see now that we have all these files that start out with the output name that we gave NAMD. So these files are the output of NAMD. We have these min beta files. And the one that's probably the most interesting is the .dcd file, which gives us coordinates for each frame of the simulation based on this DCD frequency, which was every 100 steps. So during the 500 step simulation, every 100 steps, it's going to write a frame. And so let's again switch VMD to our working directory. So I just need to do cde:/teaching/md. OK, and then I can do an ls here, and we see these files. So, so first I'm going to load the PSF file, which gives all the information about the atoms that we need to load the later load the coordinates. So that's beta sol.psf, and I'll hit load. And then now we're loading files for beta sol.psf, and we're going to load the frames from min_beta.dcd. So then I hit load, and now we can see, we have 5 frames as we expected. So this first is at 100 steps, 200 steps, 300 steps, 400 steps, and 500 steps. We can see the water moved moves around a little bit during this simulation or during this minimization. Let's look at the protein. So if we zoom in here, I'm going to turn off depth queuing, make it a little brighter. So yeah, we can see that the protein definitely changed, moved around a little bit during this minimization. You can see that this lysine side chain moved closer into a hydrogen bond with the backbone here, which maybe wasn't present in the initial structure. Went from being 2.85 angstroms to 1.83 angstroms. Okay, so I'm just going to leave VMD open now. I'm just going to get the windows out of the way here. Okay, so the results of our minimization are these restart files that we can use then to start a new simulation with NAMD from the coordinates and other parameters of the system. So the three important files here are this min_beta.restart.core. So those are the coordinates that we have at the end of the minimization. That's what we want to use to start our simulation. So to do that, we're going to uncomment this bin coordinates and change it to that file name. So it should be min_beta.restart.core. The bin velocities, well, so if we were restarting a molecular dynamics simulation, we would want to restart with the velocities. But during minimization, there's no real velocities anyway. So I'm going to leave this commented out, though. Maybe I will change this to min beta vel, but it won't be red because we have this comment character. And then the extended system, that's this XSC file. That's the size of the system. And we can just adapt that from the minimization. So because we are getting that value from the minimization, we no longer need these cell basis vectors. So we're going to delete those. And then for this simulation, it's no longer a minimization. So we're going to call it EQ_beta. While I'm at it, I'm going to do save as and save this as EQ_beta.NAMD. So it's good to keep all of your files so that you know what you did. So I'm making a new file for this equilibration dynamics run. So to make this dynamics, we need to take minimization on and delete that and change this. And in the assignment, I asked you to run 10,000 steps. So we'll change num steps to 10,000. And I think that's all we need to do to run the molecular dynamics simulation, this equilibration simulation. So I'm going to hit save. And I'm going to go back here and do NAMD2. And it's called EQ_beta.NAMD.txt. Okay, so now I can see it's running. I got some energy output here. I can see the temperature is roughly 295. Okay, so now it's run 100 steps. See the temperature is only 188 Kelvin now. That's because we started from the minimization. So this Langevin thermostat is going to make sure the temperature rises as the simulation runs. So at 200 steps, it's already 200. And we should get up to 195 after a few steps. So the, or 295. the time step is 2 femtoseconds. So every 100 steps would be 200 femtoseconds. And this 10,000 steps then is 20 picoseconds. So I'm going to let this run for a while. Okay, so now the simulation has completed. We've run 10,000 steps. You can see that temperature in the last frame was 290. It can go to the last, the earliest frame I see here. It was also somewhere around 290. It should fluctuate. So here it's 294, 291, and it should fluctuate around 295. Okay, so now we can load that into VMD. So we'll do, so we've already loaded the minimization. But I'm going to delete the minimization. So I'll go to delete frames and just hit delete. And now we have 0 frames again. And then I'm going to right click again on this molecule and do load data into molecule. And I'm going to select now the EQ beta.dcd. Okay, so now we can see a little bit of the simulation. We can see quite a bit of movement. I'm going to show some water here. So I'm going to show the water that's within 5 angstroms of the protein. Then we'll go to trajectory, update selection every frame. Maybe I'll turn that off so we can see how the water diffuses over time. Doesn't diffuse that much, I guess. Or wait, there we go. Yeah, so so this was the water that was within 5 angstroms of the protein at the beginning of the simulation. And you can see that this water spread out a bit into the box during the simulation. So this was 200 picoseconds. So that gives you an idea of how far water can move in 200 picoseconds. We can also look at the ions, see what they did during the simulation. They also diffuse somewhat. So this is really a movie of what happened during the simulation. Okay, so this NAMD output, I asked for the miscellaneous energy, and you can find that by using this key here. So miscellaneous is in this column, and it's the second one down. So you can see what the value is right here. It's 0, and the total energy is the third down in the first column. And there's other energies like van der Waals, potential, kinetic energy. Okay, so the next thing we're going to do is calculate the RMSD as a function of time during the simulation. So this will tell us how the conformation of the protein changed during the simulation. So to do this, I'm going to write a TCL script in WordPad here to run the to analyze the simulation. So I'm going to do new, and so what we want to do is we're going to step over each of the frames, and we're going to calculate this RMSD from the original structure. So to do that, we need to load the original structure. So I'll say set ref mol, mol new, And the original structure was, what was the PDB file called? 1E0M. Okay, and then I'm going to do $ set ref cell atom select ref mol name CA. So for this RMSD, so it's going to be the root mean squared deviation of the atoms from their original positions. I'm going to use just the alpha carbon atoms to calculate that difference. This is something that's typically done so that side chain movements are ignored. Okay, so then I've made that selection, so then I need to load our new, next molecule. So I'll just do mol new and beta sol.psf. This was the PSF file we used in the simulation. Then I'll do mol add file, eq beta.dcd. We can also include the minimization. And maybe also the original PSF file. For that one, the deviation of the atoms from their original position should be 0, but it's a nice check. So I'm going to first load the PSF, then the PDB that we had originally, then we'll load the trajectory from the minimization, and then we'll load the trajectory from the simulation. I need to make a selection of atoms for this. So I'll do atom select. This will be the top molecule, name CA. So these two selections have to have the same number of atoms, the reference selection and the selection that we're going to use for the calculation. Okay. All right, so I just got rid of some of the space there. Okay, so then I'm going to loop over the frames of the simulation. So to do that, I'm going to first set the number of frames to a variable. So I'm going to do set n equals mol info top get num frames. So that will get us the number of frames that in the top molecule. Okay, so then I'm going to do a loop. So starting at I equals 0 until $i is less than $n, increment I. So this will just count from 0 to n, where n is the number of frames. Well, actually, it counts from 0 to n minus 1 because the frames go from 0 to 99 since we have 100 frames. And we start counting with 0, as is often the case in programming. Okay, so then we want to, the protein itself moves a little bit during this simulation. So we want to make sure that we ignore any overall movement of the protein and just look at how the conformation changed. So yeah, so the protein will move and it also might rotate, but we're going to ignore the rotation and movement because that's sort of arbitrary for how we started our simulation. And we just want to look at the changes in the internal degrees of freedom. So to do that, we can have VMD create a matrix for us that does the best transformation from our current structure to our initial structure. So it'll do the best displacement and rotation. And then when we calculate the RMSD, we're only considering the change in internal coordinates and not the overall displacement and rotation. So I'm going to call this matrix M, and to do that, we do measure fit, and we will give the selection, which I'm calling SEL, so $SEL, and then $ref underscore SEL. And so this matrix will be the matrix that, if applied to the selection SEL, will make it as close as possible to the reference selection ref SEL. And so then I'll do set RMSD. Oh, well, first I have to actually transform the structure. So I'll do $cell move M. And so that will actually just move the these alpha carbons, which I guess is okay for calculating the RMSD, but it won't be very nice to look at. So actually, I'm going to make a new selection, atom select top, all. So this will select all of the atoms in the simulation and include them when it does the rotation. Or maybe, yeah. OK, so then we'll do all move here. Not necessary, but it will make the result easier to look at. OK, so we're going to move each of the frames so it fits best with the reference. And then we're going to calculate the RMSD. So I'm going to do set RMSD, measure RMSD, cell, ref cell. And then I'm going to type puts I RMSD. So this will put so this will write for each frame. It will write the step number or the frame number I and the RMSD value. So I'm going to save this as needs to be as a text document, and I will call it rmsd.tcl. OK, I'm about to save in text-only format, and that's what I want to do because this is programming. OK, so now let's see if that works or if I made some mistake. So to run that script, I'm just going to do source rmsd.tcl. Now it's .txt, but that's fine. OK, so, oh, well, I forgot something. In fact, OK, so I'm going to delete these two molecules and go back to what I had. And when I did this add file, I needed to add wait for all. Wait for all. Wait for all. So that means it will wait until it's loaded all of the frames of the DCD file before it starts doing the calculation. So let's save that. And let's try it again. Source rmsd.tcl.txt. OK. Okay, well, it appeared to work, but it's always giving me the same number. So why is it doing that? Oh, so I'm counting from 0 to 99, but I'm not actually setting the frame to that number. So we have to tell VMD to set the frame to that number. So I'm going to delete these molecules again. And I need here molinfo top set frame I. So here we're counting from 0 to 99. And then here we're actually telling VMD to set the frame to whatever I is. So that's important. So, so this should run through. Now I'm going to save that again, and let's try it. And it should run through all of the frames. And see, now it's actually changing. OK. So we start out with some number that's very low. It's like 1 times 10 to the -7th. So it's effectively 0. And then it goes to 0.1. And by the end of the simulation, it's something like 0.9. OK, so I'm going to write this to a file. So I'm going to do set out open, and we will give the name of the output file. So I'll call this rmsd.dat. And W means I'm going to write to the file rather than read it. So this variable out represents the stream that I'm writing to. So here I can do puts $out. And then at the end, I want to close that file. So then instead of writing it to this terminal, it's going to write it to a file. So now we get no output, but now we should be able to see if I refresh it, should be able to see rmsd.dat. So I'm going to open that with WordPad. And then we see the RMSD as a function of frame number. But actually, we would like to convert this frame. We'd actually like to know what the time is rather than the frame number. So I'm going to now change this script. Oh, I guess I closed WordPad. OK. OK, rmsd.tcl. OK, so I'm going to change this to, instead of writing the frame number, to write the time. So I'm going to make a new variable here, set t. And how do we calculate the time? Well, so the time step is 2 femtoseconds. So we do 2 times the number of frames, or the number of steps per frame. So that was this variable called DCD frequency, or DCD freak in the config file. And that was 100. So every 100 steps, we wrote a frame to the DCD file. So each of these frames represents 100 steps. So each of these frames represents 200 femtoseconds. And then then this will give us the time. To do any math in TCL, we need this expression command. We don't actually need these curly braces. So then we'll multiply that times $f, or $i. So for each frame, we multiply times 100 and times 2, and that will give us the time in femtoseconds. If we want the time in picoseconds, then we need to multiply times 1 out of 1,000, or we can just say divide by 1,000. Okay, so that should give us the time. So then I'll replace this $I with $T. And that will write the time in picoseconds. So let's try that. Okay, so now I'll open rmsd.dat again. Okay, so now this is the time in picoseconds. This is time 0. Well, this is minimization, which doesn't really have any time associated with it. But in any case, you can see that these are, we ran 20 picoseconds, which was 10,000 steps. Okay, so now I'd like to plot this. I suppose I can plot it with Excel. Again, not the best program for plotting things, but you know, most people have it, so I will do it that way. Okay, teaching MD. And I want all files. And I'm going to select rmsd.dat. Okay, so it's going to, so this is delimited. And I'm going to need to tell it how it's delimited. So this is delimited by spaces. So then I'll select space here. So now it's going to put the time in one column and the RMSD in another column. So that's good. So I'll hit finish. And there we go. So now we have the time in one column and the RMSD in another column. And I guess I will select all of this data and plot it. I haven't used Excel for a long time. I hit right click. Quick analysis. Charts. Line. All right, there we go. Okay. So this is the RMSD as a function of time. The time axis has a fairly terrible formatting. So let's go from scientific to general. Okay, that's fine. Okay, so this is my plot of RMSD as a function of time. And you can see it quickly goes up to about 1, and then it stays there. So the structure of the protein is fairly stable during the simulation. It stays fairly close to what we started out, 1 angstrom. RMSD is not a big value, but it's sizable. Okay, so I think that's all of the things that you'll need to finish the assignment.